Hello, everyone. Welcome back to the next lecture in our continuation of eigenvectors and eigenvalues. In the previous session, we discussed, or the theory was about what are eigenvectors. So, just to recap, eigenvectors are vectors which, when stretched in a particular direction, which means either if they are stretched or shrinked, they do not change their directions. So those are eigenvectors. They have momentum, they have magnitude. Okay. So, like for example, velocity. Now, what are eigenvalues? They are a special set of numbers. So basically values, which means they are numbers. And why are these numbers important? First of all, these numbers are associated with a square matrix. So what is a square matrix? Which has same grid. It's a grid with same number of rows and columns. Okay. So say 3 by 3 or 5 by 5. So that's a matrix. They tell a lot about the properties of the matrix, especially like what happens when you transform, rotate. Okay. So how a linear transformation represented by the matrix stretches or shrinks in certain directions. So eigenvalues tell them. So certain important points, linear transformation. Okay. So like say imagine you have a machine that takes shapes, okay, which stretches or shrinks. So this machine represents a linear transformation. So when it's shrinking or stretching, it's transforming. Now this can be described by a square matrix, the machine stretching and shrinking, which means either the vector is moving forward or it's moving back. Okay. And eigenvalues tell you how much of this movement is happening, how much it's going up or how much it's going down, okay, in a certain direction when the linear transformation is applied. And again, in which directions, okay, it's not any directions, these are special directions, okay, which means the direction do not change associated with the eigenvalues. Now, one another important point to note, there can be multiple eigenvalues and eigenvectors for a single matrix, depending upon its size and properties. So let's say what we are discussing. Say, for example, take a trampoline. The trampoline itself is a matrix. Okay, so trampoline is something on which you jump up and down, right? So when you jump up and down, the transformation changes. Okay, so the eigenvalues would be different stretching factors like how much you bounce in a different directions. So the more you press, okay, the more it goes down, which is the highest amount. Or where if you just kind of slightly walk on the trampoline, it does not shrink as much, right, as compared to jumping, because when you jump, you put more pressure, right, on the trampoline. So these are eigenvalues. Now, where are these used? Okay, applications of a square matrix, eigenvalues and eigenvectors, like where are they applied in real life? In a system of communication. See, almost all the fields, like it is also applied in computer science, machine learning. Okay, so in communication, when you construct a bridge, okay, the smallest magnitude of eigenvalue of a system that models the bridge, okay, is the natural frequency of the bridge. Okay, automobile stereo system design. These are just some examples, not all the applications. Okay, so where it aids in reproduction of the car vibration caused by the music. You want more vibration because you feel good. The ding 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 ding, the sound that comes in the car from the car audio. When you're driving at a high, when you're playing your music at a high volume, all the windows are closed. That way, it is also used in electrical engineering, okay, to decouple a three-phase systems. In mechanical engineering, okay, it helps us to decompose a linear process into smaller manageable tasks. Okay, so say if when stress is applied to plastic, the deformation can be divided into particular principal directions. Like you can guess how much the plastic would stretch or solidify in which direction. So you have seen the importance where these eigenvalues and eigenvectors are used. They are also used by oil companies, okay, in order to determine from where they can drill the oil before that. So n number of applications of these. That's why they are so important. So this is the explanation in simplest terms without using any mathematical jargon. Then in the next slide, we go into the mathematical details, okay? So imagine you have a special machine that either squishes or stretches a shape, okay? So either it compresses or stretches a shape, so that's the machine. And the eigenvalues are little secret settings on this machine that tells you how much shape gets stretched in a particular direction. Okay, so how do you find these settings? First, you have the machine blueprint, which is the matrix. Okay, you have a blueprint, which is the matrix for a machine. The blueprint is a table of numbers, right? Matrix, rows and columns. The magic trick to find the secret setting, which is the eigenvalues, what we do a little trick. We apply certain mechanism. We create a new blueprint, okay, which is a new matrix based on the original one. So we take the diagonal from the original blueprint. Okay, again, just imagine. Next slide, we have all the mathematical concepts or how to represent it mathematically. Original blueprint, okay, original is diagonal, okay. Then we subtract a special number, we call it as lambda, and this is its symbol. From each number in this diagonal slice, we copy the rest of the numbers from the original blueprint, move into the new one. Okay, so we have a diagonal, we have the original matrix, we copied it into the new one. Now finding the sweet spot. Now this magic trick helps us find the special lambda values, which is the eigenvalues. First, we set the determinant of this new blueprint to 0. Okay, it's like a special code that tells you something is important. Okay, setting it to 0 helps us solve the quadratic equations. Okay, and then you solve the equation, quadratic equations. So very simple. So basically, it's a machine of which settings you need to find, which will either stretch or squeeze anything in a specific direction, any object in a specific direction. So now, here is the mathematical terms, right? So imagine a square matrix A. So the matrix name is A. So here it is, the matrix, and these are the eigenvectors. So this has to be true. A times the vector is equal to lambda times the vector. So matrix, this is the eigenvalue, okay? So now here, what we do, AV is equal to lambda V. We begin with that, okay? Next, on the right-hand side, we insert an identity matrix. So remember how we discussed in the previous one, we take a diagonal of it. So what is an identity matrix? It's a matrix which all the diagonal values are 1 and rest all the other values are 0. Okay. Again, what is identity matrix? Matrix whose only the diagonal values are all 1 and rest all the other values of the matrix are 0. So when we bring this here, so if they're equal, this minus this should be 0. And then, which means absolute value of V and V cancels out in this from this equation. So what we are left with, A minus lambda times I should be equal to 0, and then we compute. Now let's see with an example. So let's say we have a matrix A. Okay, it's a square matrix because it's 2 by 2. The matrix is 2, 1, 4, 5. These are some values. Okay. Now, A lambda times I, okay, I is identity matrix. So which is, the identity matrix would be 1, 1, 0, 0. So if we do A minus lambda of I, we would get this. So 2 minus lambda, 1 is because it's the identity matrix. 4 stays same because only these would be 1 for the identity matrix. And this becomes 5 minus the lambda. Okay. Now what we assume, this is equal to 0. So this should be equal to 0. Now what we do is cross multiplication, 2 minus lambda times 5 minus lambda minus 4 times 1 is 4 is equal to 0, which when expanded, 2 5s are 10 minus 5a minus 2a minus 4 is equal to 0. Lambda square, okay, this is lambda square minus 4 is equal to 0, which leaves us to lambda square minus 7, which is minus 2 minus 5 becomes minus 7 plus 6, because 10 minus 4 gives us 6 is equal to 0. When you solve this quadratic equation, you get either lambda minus 6 should be 0 or lambda minus 1 should be 0. Okay, so then, which means either lambda is equal to 6 or lambda is equal to 1. Hence, the required eigenvalues are 6 and 1. Okay, one more time. So we have this thing, given matrix A, identity matrix is 1 0 1 0 0 1. So that would be the identity matrix. We take this, we expand it, we get this. Okay, 2 minus lambda 1 4. Okay, 5 minus lambda. Then we assume we take the absolute value of this equal to 0, which means this is equal to 0. We multiply, do cross multiply, this multiplied by this, 4 multiplied by this. Okay, subtract should be equal to 0. We get this after expanding. Okay, then we solve it, this quadratic equation, and given this value, we compute lambda is equal to 6 or lambda is equal to 1. Okay, so this is how we find the eigenvalues. So hopefully this helped. You can do some more examples, take some more matrices, just assume some matrices, okay? Apply this formula, try to compute it, your eigenvalues, okay? That is all for today. See you all again in the next lecture. Until then, happy learning. Thank you for your time.